Hello, Seattle Prep Stats. It's wonderful to see you on this. Well, it's Sunday night when I'm recording this video, the day before you guys come back. Um, uh, Welcome back. And now that this is our reality for the next several weeks, making the most of it. You've got my Leitrim banner up there, flag up there. That's the county in Ireland where my grandmother was born. And I actually visited her, like the plot of land where she grew up. And back in 88, I think. Yeah, that's good math. So it's the podunk of Ireland. It's like the North Dakota of Ireland. There's nothing there. There's nobody there. It's just kind of a thing. Anyway, so we're just going to quickly go over the test. I saw that I made this key, but I couldn't find a video. So unless I recorded a video and I've forgotten about it, I thought I should go through things with a video just so I talk about things a little bit, and so you can get this information. So this was the test you took back before break, and here you go. So relationship, big things to talk about relationship. You're going to talk about the direction, positive, negative, kind of association. Is it straight or is it curved? You're going to talk about how strong the relationship is. Is it adhering to that pattern that you see, or is it kind of scattered all over the place and it's a very loose pattern? And then finally, outliers. So those are the things I mentioned. So there's a negative association between temperature and latitude. The pattern is fairly strong and linear, though there is one outlier. And I looked it up and said Phoenix. If you didn't say Phoenix, you'd be fine. But I just looked it up, and Phoenix is the outlier. Phoenix. Never lived there. I wouldn't live there. If you want to live there, it's up to you. Identify the slope of the least squares regression line in this context. So you just have to go to the equation, and the equation, I gave to you right here. I gave you the equation, so you just had to read it. And then the equation, the slope is 0.782. And so this is how far the y goes up for each additional value of x. And so for each additional degree of latitude, the temperature is predicted to be 0.782 degrees less on average. So important things about this is just like identifying the slope, using the context, and then clearly indicating that you're talking about the model and you're talking about on average what's going to happen, but there's going to be variability. There's going to be noise in this. And so, that was important. A little bit of acknowledging the limitations on the model. Use the model to predict. Just can you use an equation? So I just plugged in the numbers to figure out what temp hat was. Find the residual. Residual is actual minus predicted. So I did that. And Detroit's average July temperature is 0.3 degrees warmer than the model predicts. And when you look at the situation here, I can draw kind of a line here. I think I can draw on this. Can I draw on this? Yeah, I can draw on this. And so, I don't know, something like this or something. And so Detroit, where is Detroit on here? Detroit, latitude 42 degrees. You can see it's a little bit above what the model might predict. I'm just guessing the model is kind of up here because of that outlier up there. Anyway, and so it's pretty close to the line, is what I'm noticing, and that's why it was so small. Detroit's average July temperature is a little warmer than the model would predict because they're so far north. The northern ones are cooler, but it's pretty close, but it's just a little bit off, and that's to be expected. Like, we're making a model, but we know this is predicting averages, or on average what's going to happen. It's not predicting what any individual city is going to be. So when you go across the US and look at one individual latitude, we know there's going to be a lot of variability in terms of the average July temperature. Here's the residual plot. So one of the cool things, remember about not having a calculator on the exam, is that you don't have to be able to make this by hand. You just have to be able to interpret it. And so these are all the residuals for all the points. Like Detroit is one of these points right here, with the 42 degrees latitude and then that tiny little residual. Probably the lower one is my guess. And so what are we looking for? We're looking for no pattern. We're looking for no like obvious like curve to the residuals. That the ways that the line is missing the points. That the ways that the line is missing the points. Okay, it doesn't. That sounds like horrible English. Apologize. Is not predictable. It's not sort of like a clear way that we're missing every time, because if there's a way we're missing, we're going to use a different model than a line. You'll find out about that today. So because it's random scatter and there's no obvious pattern, then a linear model seems reasonable. So that looks good. Here is the relationship between latitude and average daylight temperature. Oh, look, that's just repeating it because I didn't want to say it again. So Phoenix is a large residual. How would the slope and the correlation change? So you're thinking about this line that would be right here. And, remember, I'm kind of guesstimating it. You could actually find the equation, use the equation to graph the line. The only thing to watch out for is that the y-intercept, is 106.5. But just remember that this is not the y-axis, because that's where the latitude is 28. 106.5 is what this model predicts if your latitude is 0, because that's always what the y-intercept is what is the y when the x is 0, or in this case, what does the model predict the y is going to be? Because remember, it's just making a prediction on average. So what would happen if this thing was removed? Well, let's take one at a time. And I was kind of flexible on this. You had to be careful with your wording because of negatives. So the correlation and the slope are both negative, and you have to say how those are changing. So I took slope first. So with this point gone, then I'm guessing that this end of the line got kind of pulled up towards it, because it's that outlier. And so it's going to try to minimize the squared residuals, or that least squares regression line. It's trying to minimize how much the line is missing the points as measured by finding the residuals and then squaring those things. And so it's going to be pulled up. That end of the line is going to be closer to that line. When that thing's gone, then that thing's going to move down. And so we'd expect the line to be more like this. And so the slope gets closer to 0. It's going to be less negative. And so technically that means it means the slope increases, because it's going from more negative to less negative. Maybe it goes from, I'm just guesstimating here, but maybe it goes from something like negative 0.78 is the slope before, and maybe it goes to negative 0.6 or negative 0.5. And so technically that's an increase. I was a little flexible as long as it sounded clear to me. I could tell that you understood the math, even if your wording wasn't great on that whole negative thing. Correlation, since Phoenix is an outlier, then removing it strengthens the linear pattern. The linear pattern is stronger, and therefore, again, it's going to... and then you say, well, what's going to happen then? Well, the slope is negative, so the correlation is negative. And since it strengthens the linear pattern, it's going to get closer to -1. So like if the correlation, I worked it out later. The correlation I worked out is negative 0.5. You didn't know that right now, but I just want to write that down. If it's negative 0.5 now, that outlier is weakening the linear pattern. So when that thing's gone, there's a stronger linear pattern. And so maybe it's something like negative 0.7 or something like that. Okay? And so I said that would make it decrease because it's more negative. R squared, so there's variability that can be predicted, variability in temperature that the linear model helps explain, and 27.7% of the variability can be explained with this linear model. That's a memorized sentence. You just want to have that thing down. Calculate the correlation, just had to square root it, but then you had to remember it's negative, and so you had to make it negative. Yeah, okay. And then I just want to make sure you could find the equation of a least squares regression line. And so here's here are the formulas. I just plug the numbers in. I remember having a little trouble with this. I get confused. So just take a moment when you're doing it. Just say, am I plugging in the right things? Maybe here's a time when you'll write the formula down to help you plug things in. Remember, you don't need to write formulas down, and often it can be a problem if you use the wrong notation. I don't think it would on this, but in other situations it is. And so, it's not always the best, but in this case, I need it because otherwise I put the wrong number in the wrong place. So the correlation was that thing, and then the yeah, I can't remember where I got this problem. Sorry, confused. No, distracted. So standard deviation of y. I'm checking it now. I did this like a week and a half ago. Yeah, standard deviation of y divided by standard deviation of x. So this is kind of weird. This number, like if you were interpreting it, and when I saw that number, I'm like, that can't be right. Like, what's going on? But remember that what that tells you is that for each additional point, on average, we're saying that the y, what's y ERA? The ERA will go down 9.92 points. But when we go over 1x, it was a little confusing here. X, they said in the problem, I got this, I can't remember if I got it out of the book or somewhere. I got it somewhere. And X is a strikeout percent. It shouldn't have said K percent. It should have been K as a decimal instead. I wonder if this number should have been adjusted. I remember I got this off, I think I got this out of off AP Classroom. And I realized there's a little bit of mistake here. So I'll interpret it. If you get something like where clearly you thought of it as 21, like you adjusted it and you said the standard deviation was something other than 0.0426, like you said it was 4.26 because of this little difference here, then I'm going to cut you slack because I thought the problem, it shouldn't say K percent. It should be K as it should be as a decimal instead. Okay, let's just come in. Okay. Right, and then so the thing is so that'd be going from 0% to 100%. So if your ERA goes from 0%, or your strikeout percent goes from 0% to 100%, then your ERA is going to go down 9.92 points, and then it kind of makes sense. And then there's the other information there, and you can see, if someone had an ERA, had a strikeout percentage of 100%, this would predict a negative ERA, which is impossible. But nobody has a strikeout percentage that high. And then this is another one where I just want to know that you could take R and turn it into R squared and get the R squared, which is 28.1. So I was asking the same question I asked on the problem page before, but just reversing the order. Just if you heard it from the other direction, would you identify it? Big thing is just make sure you understand that this correlation isn't causation. So you can't say cause and effect on this stuff. And that's just a set thing all year. You know, you read those questions when they ask a question like this and say, are they implying cause and effect? And finally, the last one was this idea that when you predict what somebody's z-score is, for y, it's r times the z-score in x. We talked about this. This is the justification that makes the slope formula make sense. Like why we have that slope formula that right here that you see there. And so if they are one standard deviation above the mean, so that's saying they've got they're a good strikeout pitcher. Then we expect their ERA to be below average, but it's not like it doesn't go lockstep. Like if someone strikes out more people, that doesn't mean their ERA is definitely going to be better. It's just on average, it's going to be better. So if their z-score, here's the formula, if their z-score in X is 1, so they're a z-score of 1 for strikeout, then we'd say, well, we expect them to be somewhat better in somewhat better in ERA, and so we give an ERA z-score of negative 0.531. So they're 0.531 standard deviations below the mean. If it seems weird that it's below, remember that if you're good at strikeouts, then your ERA is going to be smaller because of that negative association that they talked about up here. And so it makes sense that you'll have a lower standard deviation because a lower z-score in ERA because a lower z-score is good. All right, that's this wacky. It's not that wacky. That's this test, and let me know if you have any questions about it. I'd be happy to answer them. And that's it. Okay. Take care. More stuff today. Pause.